Hello, everyone. It's my pleasure today to introduce Mark Cutkosky. Mark is the Fletcher Jones Professor in the Department of Mechanical Engineering at Standford University. He got his PhD from Carnegie Mellon in the Mechanical Engineering Department. And since then, he's been working on a lot of really interesting bioinspired fabrication design approaches for manipulation, sensing, and a variety of other applications. You may be familiar with his work from when it's been featured in the Discover magazine, New York Times, and a lot of other venues. For this work, he's also been awarded the NSF Presidential Young Investigator Award and the Times Magazine Best Innovation. So please join me in warmly welcoming Mark Cutkosky.
Thanks. First of all, it's great to be back at UPenn after a few years, and there are a lot of people here that I know. It's always a great place to visit. I thought today what I would like to talk about is soft robots and their interaction with the world. Soft robots, soft robotics is a really hot topic nowadays, in part because many people have discovered they can make soft robots, and that's very exciting. Although to some of us it's sort of like, well, yeah, but I feel like we've been doing kind of quasi-soft robots for 25 years. So, but what's interesting is that they're almost never entirely soft. They're always sort of selectively soft in certain directions. And that's essentially the theme that I want to talk about today. I'm going to start out with some fairly old stuff just to sort of explain what I'm talking about, what the principles are, and then I'll end up with a couple of very new projects that I'm excited to share with you. So this little sort of screensaver that I am playing is a nice example of a system that needs to be kind of selectively soft in its interaction with the world. All right, so I'm going to lead off with a cartoon that when I was a graduate student at Carnegie Mellon, I saw this in Punch magazine. I loved it. It was my favorite cartoon because it described exactly what was wrong with robots at the time, and which I'm sorry to say is still pretty much what's wrong with robots today. The world is a homogeneous, flat half space with a uniform coefficient of friction. You could do non-holonomic motion training on it. Oh. Okay. So, in contrast, when you look at animals, one of the things they're very good at is coping with these sort of unexpected deviations from your nominal plan of the world. Nature is not optimal, but it is very robust. And so we've worked on and off over the years, partly with Dan Koticek in the audience there, but also with Bob Full across the bay at Berkeley. And Bob will point out that there are these sort of recurring things we see when we look at how animals interact with the world. They're very complicated systems. Your immediate reaction when you look at anything, even a single cell, is actually very complicated when you think about the little microphages and the sodium channels and the protein folding. It's like, oh my God, there's no way we can do that. Well, you're right, there's no way you can do that. Fortunately, you also don't have to, because what you also see in nature are very nice ways of taking complex systems, simplifying them, treating them as though they were quite a bit simpler. And so you can do those systems in your robots. You also see that animals, because they have to survive and not starve. They're very effective at managing energy in their interactions with the world. And then the two that I've highlighted in red at the bottom is that you see that they always use multifunctional materials. Most man-made stuff that we have, we take fairly uniform things and we assemble them to get the behavior we want. But everything in nature is variable. So if you think about like a crab or a lobster has a hard calcified exoskeleton, right? Well, yeah, except not at the joint. It's very elastic at the joint. And that kind of variation from hard to soft, back to hard again, is something that we see all the time. And finally, animals don't just survive variations in the environment, they exploit it, they take advantage of it. We really need to learn to do that with our robots as they go out of, say, a manufacturing environment and into the world at large. So those are the things I'm going to focus on. And just, again, thinking about soft robotics, I saw this, I was talking with David Hu, and he was showing me one of his papers. They've been studying tongues. And it's a great example. You think of a tongue, you know, it's this classic sort of soft robotic structure. It's a muscular hydrostat. It's very many degrees of freedom and sensors. But you know, there are animals like lions and penguins where the tongue has these really hard keratinized spines in them. And it's useful, of course, for hanging onto and stripping meat off the bone. And so what we find when we build structures, like spiny robots with that climb and have spines that they're soft, is that, like these animals, we want things that are mostly soft, but also have some fairly stiff, hard elements like spines, or you know, an octopus which has a beak. And we do that because it improves our interaction with the world. It improves our performance for certain tasks. And you pay a price for that. Whenever you try to combine, you know, two materials with very different Young's modulus, inevitably you get stress concentrations at that interface, which you have to manage. And so you wind up putting in fibers and having gradations of material and special designs and so on to make that possible. And that's just been a recurring theme year after year in the robots we build, is how do we introduce these very disparate behaviors into a robot. So what I see when I look at the field from afar is that it seems like we start out initially with what I call no-touch robotics. We have little drones that fly around, and the whole thing is to make sure that they don't crash into things, that they stay away from obstacles and don't bang into things. And so if that's the case, what can you do? Well, you can take video, and you can do slam, and you can do slam, and you can do slam. And that's about it. Or the first mobile robots. It was all about, again, wheeling around and doing slam and building up maps of buildings and using your ultrasonic sensors so that you didn't bump into things and get into trouble. But what is happening as you get greater and you learn more is that you start to interact energetically with the world. So this is Alexis Lucier-Vivienne. He was the first guy in our lab to do perching, initially with fixed-wing airplanes. So you fly and you land on the wall. Bam! You have to absorb that energy and stick and not bounce off. Or Dan Golden with his very nice sandfish robots, swimming in particles and really modeling that interaction. Or this is actually a brand new thing. We're working with Chris Hauser at Duke University and JPL making soft and spiny hands for Robosimian, which is this huge 100-kilogram robot, and we want it to climb steep, rocky surfaces. And so, sure, you want soft robotic structures that will conform to surfaces, but you also want spines, because actually spines work incredibly well on hard rock. Well, then how do you marry these two very disparate technologies together? Or, I love this one on the bottom, which is Rex having an absolutely wonderful time in its mud bath here, interacting gloriously with its world. So great, we're talking about robots that interact, and of course in all cases this means really modeling that interaction with the environment. And so a lot of what we've been doing sort of is really focused right on that problem. How do you model this interaction with the world? So what I see, and this again is an old image from Dan Kotichek and Bob Foll, is that in natural systems, it's your approach to dealing with that is that it's all coupled. You don't have a structure and then some sensors and some actuators and a controller. That's nice, it's very modular, but that's not at all the way it is in nature. Sensing and actuation and control and passive mechanical properties are all intimately intertwined. So the cockroach benefits a great deal from this sort of first-order passive response. In fact, it's stable, you can show, passively as it runs. And then, of course, it also has actually a very rich suite of mechanoreceptors and other sensors that close a loop around through the neural system. All right, so that's one theme. Another theme I want to talk about is that if you're going to build robots that have these functional materials with varying properties, you of course need manufacturing processes that will let you do that. Our original manufacturing process, our go-to process, was something called shape deposition manufacturing that came out of Carnegie Mellon and Stanford. And the process is basically that you deposit material and then you shape it, You can, at that point, add discrete components like bearings or microprocessors. You can then add a sacrificial support material, cast in the next layer, and so on. We, to be frank, we use it less and less. And the reason why is that it's slow, and also the reason why is that 3D printers are getting better and better. They can do multiple materials, soft and hard, the resolution is getting better. We still use this for certain special things. For example, if you have a little robot, like a little cockroachy robot, with leg joints that's running at, let's say, 10 cycles per second, it doesn't take very long to build up millions of flexing cycles, which means fatigue is a problem. And one of the things that SDM will give us is that I can make a mold where you get like a glass smooth surface finish. And that absolutely helps fatigue. We have not yet been able to 3D print anything for flexures for little robot legs that will last as long as the ones that we make using this approach. But this way, if I do it, because it takes a few hours for the polymers to cure before I can do the next layer, you know, it will take a couple days to make a fairly complicated part. So it's not the best compared to printing. Yeah,
It's after this, but can you tell us why the surface finish is?
oh, totally. This is that
Same
practice
Griffiths
thing that we were talking about at breakfast, Dan. If you want to avoid fatigue, having a glass smooth surface finish is absolutely helpful and important. And there are other things you can do like shot peening and so on. But for these polymers, just the little digitization you get from 3D printing is enough that the parts won't last as long as the ones you can do by SDM. So we still use it. For example, Hannah Stewart, who just graduated and is now a professor at Berkeley, she did the underwater hands for Ocean One. And most of them are 3D printed, but the joints of the fingers are still done by SDM. All right, so it also gives you now, with these materials, the ability to have desirable properties for your interaction with the world. And this is an old slide, but I still like it because it's a nice example of what I mean by selectively soft. So actually, I think this one on the right hand is from Jonathan Clark. Here on the left, we have an isolated cockroach leg. And that's actually one of the nice things about cockroaches is you can pull off the leg and keep it hydrated, and you can put little wires in it and it will continue to function for a while if you keep it hydrated. And on the right is our approximation for one of these little robots. So the clear material, the transparent, is a hard, a stiff polymer, kind of like a polycarbonate or whatever. And then the pink material is quite soft and elastic. So although the structure of this leg doesn't look at all like the cockroach leg, it actually has quite similar behavior. And it has similar behavior not only in terms of its kinematics and stiffness, but also damping. We intentionally chose a polymer that is viscoelastic so that what you see here with the cockroach, the vertical axis is force and position. So as you load it up and you unload it, there's this loop hysteresis. The area inside the loop is energy loss per cycle. And you can prove that this actually stabilizes the cockroach when it's running. And we intentionally picked a polymer for our little robot that had a similar behavior. And actually it was Jorge Chan. If any of you know who Jorge Chan is, you know him from the comics, PhD comics. But he was a good researcher too. And he was able to show that the range of frequencies over which you can run your little robot and have it be self-stabilizing is actually much broader when you do use these sort of energy-absorbing materials. So that's what I mean by sort of selectively soft robotics. All right, now I'm going to go to my poster child that's a sort of a jumping off point for the new work that I want to get to in a little bit. Well, as I said, your first reaction when you look at anything in nature is that, oh my God, it's incredibly complicated, we can never do that. And you're right, you can never do that. So here's a very nice slide from Keller Autumn. For my money, the #1 expert on geckos in the world and their adhesion. And what you see in a gecko is this very interesting hierarchy of structures. So at the centimeter scale, it conforms, and then you have cetal shafts, and it finally branches down into these little spatular tips right here, 200 nanometers. We actually don't have any thing that will quite replicate that. We came close using something called a nanoscribe, but it's a digression. We came close collaborating with some people who had a machine called the nanoscribe that actually will get down to 350 nanometers. In the end, the structures didn't seem to work any better than the ones we were making, more with a micromachining method. And the killer was that it took 8 hours to make 100 by 100 microns worth of features. So it wasn't exactly a practical process. All right, so you can't do this. So what happens? What you do is you go through this process. We've done it a number of times, and it does feel like there's a pattern to it. You are faced with some challenge, like you want to climb walls, or walk on the ceiling, or perch, or whatever. And so you look in the world of nature and say, well, how, are there animals that do this really well, and how do they do it? So climbing on walls. And you would like to climb on various surfaces and so on, and you say, well, okay, what animals can do that? Squirrels can do pretty well on many surfaces. Snails can climb almost anything. Actually, there is a snail robot out of MIT. They're not super agile, however. Okay, well, Gecko. Gecko is the poster child for being agile on vertical surfaces, 1 meter per second. You talk to biologists. As I said, it's all terribly complicated. Oh my God, we can never do that. So you make some hypotheses about what you think is really important, and maybe I could just focus on those things. And then you implement it with your robot. And here, by the way, is where something's in it now for the biologists, because if the hypothesis that you make is correct, and you try it on a robot, it is much easier to test it on a robot than it is on an animal. I had a PhD student named Sean Daly who, toward the end of his PhD, he was working between my lab and Bob Full's lab. So he spent 3 days a week at Stanford, and then he'd go over to Berkeley and spend 2 days a week in Bob's lab working with these giant death's head tropical cockroaches. They are literally about this size. But they're big. And he would spend all morning putting little tiny tungsten wires into the cockroach, and by around lunchtime he's ready to put it on his little cockroach treadmill. Tired that day, wasn't really feel like running. And unfortunately, that happens all the time with biological experiments. And the robots, if they work well, they're somewhat better than that. And we test and we analyze and we look at the results. And we use our rapid prototyping to help us build it. And of course, we never get it quite right the first time. So we refine the hypothesis and we go through 1 inch iterations. So that's the process that's been behind sticky-bot robots and robot hands and walking and flying and all that stuff. All right, so let me use the sticky-bot example. It's probably the most famous alumnus of our lab to sort of make a point. All right, when we started this work, we knew right away, we knew a priori that this idea of conforming intimately to surfaces was going to be important, because we're using van der Waals forces. That's this weak interaction between electrons in the outer shells of the atoms in a molecule. So you have to be within molecular distance, really, for van der Waals forces to work. Nanometers. And so therefore you really need intimately to conform to the surface you're trying to stick to. Otherwise, that's why van der Waals forces mostly does not occur. On the other hand, if you have a sticky surface that you press and it flows and conforms, then it works. And that's mostly how Scotch tape works, is mostly actually van der Waals attraction. All right, so conformation was important. So we have toes that can conform at the scale of centimeters, and then we have a microstructured adhesive that conforms at a finer scale. This is a little forest of wedges, about 40 microns at the base, tapering to a sharp tip around 1 or 2 microns. And the trick is that when they first come in and make contact with the surface, the area is very small, so they're not sticky. And then when you apply a shear load, they bend over, and I have a lot of contact area, and that's what makes them stick. The other interesting thing with the Gecko and our adhesives is that they're directional, and we actually didn't understand how important that was when we started. So I'm going to show a couple slides to talk about why, because it's what makes the adhesive controllable. It's actually super important. And then finally, given conformation and given a controllable adhesive, you set up a control system to balance forces to do what you want to do. All right, so this is a slide from Keller again. This is real Gecko setae. And when you drag them in their preferred direction, the way they're meant to be pulled, you get their normal, there's force on the vertical axis. You can see quite a bit of adhesion. But if you push them, so they're meant to be pulled this way. But if you push them in the opposite direction, you get no adhesion at all. In fact, you just get Coulomb friction. So that's interesting. That is a principle you could exploit. So I didn't, I don't have a sticky bot that I can bring in. I did bring a piece of the adhesive. I saw that in your lecture schedule that Elliot Hawks is coming a little later in November. I hope he doesn't show the same thing. So here's a piece of the Gecko adhesive. You'll have to trust me that there's a forest of little wedge-shaped structures on there. They're too small to see. And it's not sticky. Because when you first bring it into contact with an object, it's just the tips of those wedges, and so it's not sticky at all. But what I've done here is I've got two pieces with opposite polarity. And so when I pull on a bar in the middle, I load it in shear, and that is what allows it to stick. So it's just fine, and it will hold this or even a considerably heavier weight. Well, that's cool, although, frankly, I could do this just as well as duct tape. Right? Except that with duct tape, it wouldn't do that. And that was the magic. That was the thing that we didn't understand how important it was when we started the Klein robot project. Because that's what makes it controllable. What you really don't want is a robot with something like chewing gum on its feet, because then it wastes a lot of energy with every step. Peeling and pressing it on and then peeling it off. If you're a little gecko, you can't afford that. That goes back to that thing I said at the very beginning about how animals have a very energy efficient interaction with the environment. And so if you now equip a robot with this, you have a very nice behavior. You put it down, it's not sticky, but as soon as you start to load it, now it adheres and you can trust it. And then at the end, just relax the shear force and it comes right off. So that was something I think we didn't appreciate how important it was, but we discovered it as we went. So let's talk a little more about that. Again, this is some data from Keller Autumn. These are real Gecko setae. And again, the vertical axis is normal force and the horizontal axis is shear force. So when the normal force is positive, I'm up here, that means I'm pressing into the wall, okay? And when the normal force is negative down here, that means I'm able to pull away from the wall. And then when the shear force is positive, which is off to the right here, that means I'm pulling downwards. And when the shear force is negative, that means I'm pushing. So let's look at that. So first of all, these are the different colors are for different amounts of preload, and the first thing you see is it doesn't matter too much. They all have the same kind of behavior that when I'm going upwards, what I see is a shear force that grows pretty much linearly with my normal force. Shear force is a constant times normal force. Does it sound familiar to anybody? Should do. The interesting part is down here, where my available negative now, normal force, is growing not quite, but almost linearly with my applied shear force up until it fails. This is when I have adhesion to work with. It's interesting, the causality is reversed. Here, I can control the normal force and thereby indirectly, through Coulomb friction, control my shear force. Here, I apply the shear force and thereby indirectly get a certain amount of normal force. All right, so yeah, when you're up here, you basically have just Coulomb friction, and down here we have this sort of interesting adhesive space to work with. And now you can use that in your control and in your motion planning, because the whole trick now is to make sure that your feet stay in what I call this kind of safe region, what we call the limit surface. So basically any vector of normal and shear force that's in this blue region will be sustained by the contact. And as soon as I go outside my safe region, I'll either slip or I pop off. All right, so we'll do a very, very simple example. Suppose that you're a small gecko, or maybe you're a small robot, and you're trying to climb a wall. But because you're not perfectly flat, your center of mass is a little bit out from the wall, right? So your center of mass is like about there, okay? So when you do the force balance, you have a green front leg and a rear blue leg. You're doing a diagonal stride, so it's like you have 2 feet on the surface at a time. All right, so they're both helping support your weight, but because of moment balance, your green foot, of course, is the one that needs to have the negative force, and your blue one is the one actually will have a positive force, right? So when I plot these in my force space, there's my green, there's my blue. And now it's not a trick question. Which of these is more in danger of failing? It's really not a trick question. I even put circles to make it more obvious. Yeah, the green, it's near the edge of this margin. It's in danger of failing. And we knew that. We knew that before we started. And so our tendency was, oh, let's favor the front feet. We'll be very careful, very gentle with them so they don't pop off. And that was exactly the wrong thing to do. What you want to do is that. You want to pull harder with your front limbs. And if you do that, you'll offload the rear limb. So the front limb will go from here to there with more tangential force. The blue foot thereby will go with less tangential force. And the optimal solution in this very simple case is where the 2 circles will have the same diameter as I've drawn it. Interesting. So that leads to an interesting hypothesis for the biologists. Do geckos, in fact, pull harder with their front limbs? It's not intuitive because if anybody here do any like rock climbing or climbing in a climbing gym? Quite a few. And you mostly climb with pushing upwards with your legs. You hold on with your hands, but the main upper force is with your legs, because we don't have that kind, unless you're a Navy SEAL, you don't have that kind of upper body strength to basically control yourself with your arms. But for this, it says that that's what we would actually look to do. So what does the gecko do? Good question. So here's some data from Bob and Keller, and let's take a moment to sort of parse what this is showing us. So the left front leg is here, right, and then the hind legs left and right. So let's see, in the fore-aft direction, that's along the wall, well, look at that. The forelegs, left and right, actually do have a larger force than the rear legs. So in fact, geckos are pulling themselves up more with their front legs. They have excellent upper body strength. Okay? And then, not surprisingly, in the normal direction, yeah, it's the front ones that have the negative normal force. That's how it's keeping itself from falling backwards off the wall. And then the right ones it's positive, just from the force balance. And finally, in the lateral direction, they're pulling symmetrically inward. And that's true. In fact, whenever you see a gecko on the ceiling, all 4 limbs are pulling inward towards its center line. If it didn't do that, because of the directional adhesion, if it didn't do that, it would fall off the ceiling. So, nice example. And finally, you can use this in your force controls. I'm not going into details here. But when we ran StickyBot, what we actually did was run it where we indeed tended to have a little more force, a little, on the front limbs. And the way we monitored it is, so this is another soft robotics thing. The clear plastic here is a hard urethane, tough, but kind of like a polycarbonate. And then this cream-colored material is quite soft. It's giving us some compliance to the limbs. But that also gives us a way of measuring force, because we've got a little Hall effect sensor and magnet set up here, so that as that creamy urethane deflects, we're measuring that deflection, which gives us an estimate of the force at these limbs, so that we can do our force balance. It turns out when you've got a 4-legged robot climbing a wall, it's very much the same kind of force control you do for a hand grasping an object. The The difference is that when we grasp an object, the internal force is in the squeeze direction, inward, normal, on the object. On a wall, your internal forces are all parallel to the wall itself. But apart from that, it's pretty much the same. All right, so, and Elliot will probably show this picture too. Suppose you want, so this adhesion thing works for little robots. There were some researchers at Cambridge University who came out with a paper proving that the Gecko adhesion really would not work for any animal bigger than a gecko, which got Elliot rather upset. Because what if you did want to scale adhesion bigger? And it's an interesting problem because, you've got the basic square cube law that Galileo first articulated. As you get larger, your mass grows as length cubed, but your feet are only growing as length squared. And so as you go to larger areas, you actually need more adhesive pressure if this whole idea is going to work. The bad news is that it goes the other way. Everybody who works on synthetic adhesives, us and Metten City and Conforming and even the Gecko, as you go to larger areas, what actually happens is that your available pressure, force per unit area, gets worse for various reasons. In fact, here's some data. This is from a paper that Elliot and Eric Eason put together using data from various people, including Keller Autumn. And so this is a log-log plot, and so here's the Gecko. So if you do an individual Gecko Siebel stalk, you get actually a quite high adhesive stress, mainly in shear in this case. As you go to a group of stalks, one lamellar clump, it actually drops. What they were able to measure drops quite a bit. And as you go to a whole toe, it gets even lower still. And as you go to a whole foot, it gets even lower still. And oh, by the way, if we want to get to human scale, this is our goal. It's the green dot here. So in that sense, the Cambridge guys were correct. You'll never get there if you want to do human scale climbing. What you need, therefore, is a way to scale your adhesion up to larger areas without sacrificing its performance. And a way to think about that is this goes back to the sort of selective compliance idea at the very beginning of the talk. If you just have compliance, that also will not get you there. There was a paper by Bharat Vishwan where you look at what is sort of an optimal array of compliant elements for an adhesive, which you can model as a whole like a hierarchy of springs. Okay, so this is good for conforming to the surface, but it won't improve your adhesion. And the reason why is you can just imagine what happens if I take that surface and push it down. Some of these elements are going to hit like the bumps first, and then you have to keep pushing a bit further before these ones, make contact with the valley. So what happens when I pull? Well, when these ones are actually going to have a higher stress on them, they will fail first. And then, this goes back to the crack thing, it's a crack propagation problem. As soon as you get a little bit of peeling initiated anywhere on your adhesive surface, it's like an avalanche. It just propagates across the whole area. So you need to find a way to suppress that from happening. Well, think about that. How could we ensure a more even loading across a large area and suppress this kind of stress concentration failure mode, which is the bane of all adhesives? As I thought about that, so here, I'm sorry, I just said what I just told you. Okay, so as I thought about that, the image that came to mind was thing from Gulliver's Travels, where he's lying down and he's held by these hundreds or thousands of tiny silk threads by the Lilliputians. And if you think about it, if you could ensure that every thread was loaded up to just a little below its breaking point, that would be the ideal solution, because then you could easily prevent Gulliver from getting off the ground. So we need something like that. We need to take every little element of adhesive and attach them all to virtual spider strings or something and carefully control the tension on every single one so that they all have exactly the same force. That would be a serious control problem. Fortunately, there are a couple of mechanisms mechanically that will do that. And yes, one of the less reverent members of the lab has called this the communist solution. From each according to his ability, to each according to his needs, every little piece of it. Anyway. All right, what kind of solutions? Well, one would be to use a phase change material. You could have a liquid metal that you put behind your adhesive pad, and you melt it, and you let it go down, and it flows and conforms like pressure-sensitive paint, and then you let it cool and harden and become rigid. And now you have a solid block that tends to come off all at once. We actually did experiment a little bit with that. It kind of works, but it takes a lot of energy, and the metal is always leaking, and most of these low-temperature alloy metals are poisonous, and so it was not our favorite. You could do a differential. Now, you know about a differential, it's in your car. It's what, when you go around a corner, it allows the wheel on the outside to roll faster than the one on the inside. However, they're both connected to the engine, and the torque from the engine is split to the two wheels. There are other kinds of differentials that let you split force. They're used in under-actuated hands. That's another kind of solution. And finally, you could use, this is non-intuitive, you could use what are called degressive or softening springs, and I'll explain that in just a minute. All right, so on the left I have a differential. It's a very old one, goes back to, I think, almost Roman times. You have a team of oxen pulling a cart, and you want it so that if one of the oxen momentarily gets a little bit ahead of its neighbors, it can do that, but the force of all the oxen is still evenly, the whole cart weight is evenly divided among the oxen. They all have the same force. So this is a mechanical differential. It's called a whipple tree. And you can do it with tendons and pulleys. You can do it with hydraulics. You can do it with gears. Differential. Sounds like. On the right is the softening springs. So these are shape memory alloy springs in this case. And you can see what happens. They all start out looking like an ordinary spring. Stress and strain, force displacement. They grow linearly. But then look what happens. It plateaus. Here's a plateau region. And you can exploit that. So let's talk about that for a minute. Here's our shape memory alloy springs, and the way it works is like this. So what Elliot actually did is he discretized, he needed basically a ping pong paddle-sized area of adhesive that would support his weight. And what he did is he discretized it into 24 little postage stamp-sized tiles. And then he attached every one of those tiles to one of these degressive springs. So when you bring this array down onto a surface, what happens is that due to manufacturing tolerances and the surface is not quite even, some of them start loading up right away, and some of them don't start loading right away, and that's the problem. That's the stress concentration distance that we saw in the slide with springs. But look what happens. These ones go up, and then they hit that plateau, and they just stay there until the other guys catch up. So in the limit, if you design it right, they all converge to this constant force, and so he knows in the limit that every one of his 24 tiles has exactly the same force line. And that was the secret, and that was how he could climb despite the Cambridge scientists. So there's the setup, there's the paddle of 24 little postage stamp tiles, there's the degressive springs, and there's a couple other interesting details. Remember I said that the problem with people is that we don't have the upper body strength? Well, we don't. So what you really want to do is use your hands to place the tile on the window and then have a rope down to stirrups at your feet so that you can push upwards and then replace the tiles. And there's another subtle point here. You notice that they actually go out a bit because you want to be leaning in a little bit through the window. There's a phenomenon on rock climbing called barn dooring, which you don't want. It's a way to lose control and come off the wall. So he wants to be leaning slightly into the wall. So he places his tiles there, that's where the force is, and then it's transferred down to his feet. And so it's actually like climbing a ladder where you just keep moving the rungs as you go. All right. And if you do that, if you're able to share the load, notice, by the way, that we start out with a much lower adhesive pressure than the Gecko has. We're not nearly as good as the Gecko. But by using the tiles, which give us a pretty even force over a small tile. And then by using the degressive springs, we hardly lose any adhesive pressure at all, and that's how we meet our goal. All right, so now I wanted to switch and talk to two new ongoing projects. We're not really doing StickyBot anymore, and Elliot has graduated and now he's at Santa Barbara. But we have an ongoing project with NASA to use Gecko adhesives in space. So as you know, there's a problem with space junk. People want to also manipulate things in space, and it's tough. You're in a vacuum, you can't use suction cups. Most of the stuff is not magnetic, so you can't use magnets. But you can use Gecko adhesives, and it turns out that the polymers we use actually work over a wide range of temperatures. So there we are picking up a solar panel, and what I'm going to show next is a short video that describes some of the ongoing work. This is a collaboration also with Jet Propulsion Labs and with NASA Ames. And let's make sure audio is working here.
The amount of space debris has been growing exponentially in the past several decades. Space debris can possibly crash into new satellites and cause catastrophe. One way to prevent this from happening is to grasp and recycle the debris before a tragedy happens, like in the movie Gravity. At Stanford JPL, we have learned from gecko lizards to make small adhesive grippers that adhere to smooth surfaces such as solar panels and fuel tanks with really little attachment and detachment effort. This is a nice solution for grappling and releasing free-floating objects. We then efficiently scaled the gripper up and added a special wrist design to enable the grasping and manipulation of large objects. Experiments have been conducted in the NASA JPL air-bearing floor, also known as the Robodome, where a 400-kilogram master robot with the gripper tried to grapple another 400-kilogram slave robot by grasping a solar panel. Either controlled by human or autonomous thrusters, the master robot successfully grappled the slave robot with only a slight push but large adhesion. The wrist acts like a non-linear cushion that absorbs energy during impact but stays stiff during manipulation. Misaligned grasping is also demonstrated here. For a full 3D floating test, we built an even larger gripper that can grasp both flat and curved surfaces with a larger safety factor. Experiments were conducted in the NASA zero-gravity airplane, also known as the Vomit Comet. In the flat gripper mode,
okay, I'm going to pause just a moment because there's something I want you to watch. So this is in this zero-gravity airplane that NASA has, where it does a parabolic flight, and Hal, who was on there, will tell you that yes, they give you air sickness pills and you get sick anyway. So he's grabbed this thing, which is sort of a stand-in for a CubeSat, and he'll manipulate a little bit to show he's in zero gravity. And watch what happens when he releases it, because the one thing you really don't want to do is accidentally impart some extra momentum to it and lose hold of it. So watch the moment of release.
gripper grasped a cubic object much larger than itself with little pressing force. When detaching, the gripper does not affect the object's motion state. This is very different from conventional sticky materials. Similar functions have been achieved with the curved gripper: little attachment force, strong grip, and clean detachment. Spherical surface grasping has also been conceptually proved with a beach ball. Although it does not require much adhesion, it does require a very tiny engagement force because it is easy to knock the ball away. Earlier this year, NASA sent several small versions of the gripper to the International Space Station for testing. We really look forward to bringing this technology to life and making more debris-free orbits in space.
All right, so let's talk a little bit about what was behind that. Well, in this case, we did not use degressive springs. We used a differential because we wanted even force at any level of force application. And instead of a whiffle tree or whatever, we use a tendon system. The whole idea is that we've got pairs of Gecko tiles connected by a tendon, and then we pull on the tendon, and then it's all one tendon with low friction ball bearing pulleys everywhere. So if the tension is the same everywhere in this tendon, then the force has to be the same on every pair of tiles, and that's how you get that scaling, again, guaranteeing that you get the same force over the whole gripper. It seems like a very clever idea, although maybe not so new as you might first think. There's a nice design by Leonardo da Vinci, and I love the Italian here. What it says is that Leonardo, who by the way did not consider the notable effect of friction in the pulleys, maintains that with such an apparatus, 17 fixed, 16 on the mobile platform pulleys, a weight of 1 unit would allow you to lift 33 equivalent weights. Yeah, notable effect, that's an important point, the notable effect of friction on the pulleys, which he did not consider. Even with our ball bearing pulleys, that essentially sets a limit to how many we can do in a single layer of hierarchy, how many pulleys we can wrap that tendon around. And then you either have to do a hierarchy or you go to degressive springs or something. That's sort of the limiting factor. All right, the other thing is, can you predict, you would like to know a priori when you go up to some surface with this gripper, how much force and how much moment you can apply to it before it will fail. So what you have to do is you need a way of extrapolating that limit surface, the one that I showed a while ago for a Gecko, the blue safe region. I need to extrapolate that to multiple pads, and I need to do this in a 6-dimensional force-torque space. And there are a couple ways you can do that, and when you do, what you get is this sort of 6-dimensional limit surface. Interestingly, it is not convex, which can be a problem for certain types of computation that can make it slower. And then you can't really visualize a 6-dimensional limit surface, but you can take 3-dimensional projections. So here's one in force in the z direction, and then force in x and y, and you see we get this kind of boat-shaped surface here, corresponding to these pads. So any force vector inside this boat will be sustained, and as soon as you go out, it will either slip or it will pop off. And the paper has more about that. So what are we doing right now? There is a plan to put some little free-floating, they're like very gentle, low-power drones up into the International Space Station. They're called Astrobi. It started out at MIT. And we have talked NASA into letting us put a little 2-arm wrist and Gecko grippers on the end of Astrobi so that they can latch onto surfaces and grab things with Gecko adhesive. And so right now, what we're in the throes of is a lot of very formal safety testing and meetings, and nothing outgassing, no sharp corners, no screws and bolts that could come loose, nothing that can catch on anything, limits on power. Also, all the software has to be very super fail-safe and so on. So we have a weekly meeting about that, and if all goes well, we hope it will be launched next spring, and it will be able to do testing over the summer. One of the things that we're kind of curious about, at the end of that video, it mentioned that a couple little tiles have been set up at ISS by Aaron Parness. Yeah, and they did some poll tests on those little tiles. And the interesting result was that they didn't seem to work as well as they did on Earth. And then they actually sent them back, and it looked like they were fine. They worked as well as ever. What could be the reason why some of these tiles are not working as well inside the ISS as they are inside JPL on Earth? Well, yeah, maybe. In fact, I am told, we don't really know yet. We're going to try to answer that question. One of the things I am told is that by astronauts who go up to the ISS is that your immediate reaction on getting there is, ooh, it smells like a locker room. It may well be that all the surfaces in ISS are now covered with a very thin layer of bioslime or something, for all we know. Interesting thought. So we'll be doing some tests and so on. So we're very curious to see what happens there. All right, I want to end with another very new thing. This is fun to talk about here because this is a direct outgrowth of some work that we started with CJ Kumar's lab. And if you haven't seen this video, you should, because it's actually a very cool video. And I'm just going to play, I don't know, maybe about half of it.
In this work, the GRASP Lab at the University of Pennsylvania presents a collaborative project with Standford University to give our quadrotors the ability to perch on smooth vertical surfaces such as windows. The gripper developed by Standford is not sticky to the touch, does not rely on penetration-based grasping, and does not use hook and loop fasteners such as Velcro. When set and triggered, the mechanism allows the gripper to be adhesive. To achieve a successful perch, it is important to regulate the position, orientation, angular weights, and velocity of the robot at impact. Our work in short.
Okay, so it's a great collaboration for us because Vita's group is wonderful at quad rotor control, and we had a very nice partitioning of the problem. Our goal is to build these little Gecko adhesive grippers that can absorb the incoming kinetic energy, use it to load the adhesive, and not bounce off, because that's what they want to do. They want to bounce off. So you want to load them up and stick. And our other job is to tell the quad rotor control people essentially what is the envelope of acceptable incoming speeds, angular velocities, and orientations, such that if you're inside that envelope, we can pretty well guarantee that it will slip. And then, of course, their job is to get inside that envelope. So, yeah, and then I think it's a nice thing, too, because quad rotors, again, if they just fly around and don't crash into things, of course that's important. But they can pretty much then take video and do mapping. But if they can land and perch, then all kinds of other things become possible. You can power down, and now you can stay there for hours doing environmental monitoring or surveillance or inspection or whatever it was you wanted to do, and then when you're done, you take off and fly home. Or, and this is brand new, this just came out like a week or so ago, you can even do like insects do and pull or push heavy loads. So this is the work with Matt Estrada, and it was another collaboration, in this case with Dario Floriano's group at EPFL. So the chart on the right shows birds and bats and insects and maximum force that they can exert while flying versus their weight. And they all kind of follow the same trend line. Pretty much anything that flies cannot exert more than about double its weight. If you try to do more, you wind up having motors that are so powerful when you go through so much battery, it just doesn't make sense. So, and in fact, our little flying drones would be on that trend line too. On the other hand, if you look at little beetles that push things, they can do much higher forces, and the reason why is that they're not relying on weight. If you did, you would be stuck because you don't weigh much, and so Coulomb friction, U times mg, is not very big, so you can't push very hard before you just slip. So all insects, ants and cockroaches and spiders, they all use some kind of adhesion, and it's a controllable adhesion too, because you have to have it release when you want it to. They either use little tiny spines, or they use spiders actually use something similar to what geckos have, stockulated with van der Waals forces, or they use an easily deployed and released sticky pad on the feet of ants. So they all use adhesion because then you have a force that scales with area of the foot, and you can do much better. So what we designed here are little robots that have gecko adhesives on their stomach, if you will. So they fly, which lets them get to a remote site. And then they attach a little hook or a gripper to an object that they want to influence, and they fly away while panning out a string, and then they clamp themselves onto the surface, and then they pull. And doing that, they can do at least 40 times their weight. So there's a little video here showing two of these guys teaming up to open a door, and I'll play that. Oh, or wait a minute, or power. There we go. So the first one flies in, it lands, and then it crawls over to the door. and slips a little hook under the door and crawls backwards, and then it latches on using an array of little microspines like we did for the RISE project. And then the second one flies in, puts a little hook on the door handle, goes down, and clamps with Gecko adhesive onto the glass. And there's the microspines. The door open. And just to prove a third one now. All right, so that's very new stuff. And I think on that note, I will finish and take questions from people. And afterwards, if anybody wants to come down and play with the Gecko stuff, they're welcome to do so.
So geckos also this amazing ability to navigate dirt.
Yeah.
Have you solved this problem?
No, not really. The interesting thing, though, is that it's actually what we've learned is that you should think of that as being on a spectrum. So our adhesives, we've actually switched materials a couple times. We're now using a rather stiff silicone rubber, like a cooking spatula. And one of the things you may have noticed about a cooking spatula is it doesn't tend to attract dirt particularly. The early days of RISE, we were using a urethane, which got dirty a lot faster. Cooking spatula, silicone rubber, because of the little squares, all I have to do is put it in contact with something that's a little bit tacky, and the dirt all comes off it onto the other surface. Oh, a lint roller, like on your suit, works really well too. So for the interesting thing about a Gecko is because it has even smaller features and an even harder material, pretty much every other surface that it contacts, the dirt is more strongly attracted to the other surface than it is to the Gecko. So if you're a Gecko, the world is your lint roller. There are a few exceptions. It was discovered that on white dry erase boards, Geckos do not self-clean. When you think about it, it makes sense. They're meant to be very easy to clean, so they don't attract. We can imagine how this might have been discovered in Bob Full's office. Yeah, so there's a spectrum. So as we go toward increasingly small distal features and increasingly hydrophobic materials, then the stuff becomes increasingly self-cleaning on a wider range of surfaces. You had a question, Dan? Yeah.
Well, so you anticipated my question. You've been eloquent about the complexity of length scales and appliances of the animals. But the other thing they have that we don't have is they have these diverse materials. And I wonder, you thought a lot about this.
They have, yes and no. They have diverse materials, very amazingly microstructured. I mean, the thing about nature is that it is built growing and differentiating cell by cell. So nature pays a very low price for complexity. All of our processes that we use, whether it's 3D printing or SEM or whatever, they're more like bulk processes. So every new variation in material properties with space is complicated. Even now, to do like a Gecko thing, you know, I have to go over to the NanoFab Center, I have to go to my lab, I have to go to different. There are fundamentally different machines that work with different length scales. You know, micrometers versus centimeters, and different processes. And so this complexity is tough for us. So yes, you look at like the exoskeleton of a crab or a lobster, and you find when you really look at it in